Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Juno, a deep dive into Jupiter's mysteries. The Juno mission, launched on August 5, 2011, represents one of NASA's most ambitious ventures into the outer solar system. Designed to explore Jupiter's secrets, the mission's primary objective is to understand the planet's origins, structure, atmosphere, and magnetosphere. This spacecraft, named after the Roman goddess who could see through clouds to reveal Jupiter's true nature, was tasked with peering beneath the thick cloud cover that has hidden the planet's internal workings for billions of years. Juno was a mission born from curiosity, aiming to answer fundamental questions about the solar system's largest planet and, in turn, shed light on the origins of the solar system itself. Jupiter is more than just a massive ball of gas. It holds the key to understanding the early stages of planet formation. As the largest planet, it likely played a crucial role in shaping the structure of the solar system. Scientists believe that studying Jupiter could help explain how planets form and why they take different paths in their development. To achieve this, Juno was designed to measure Jupiter's gravity and magnetic fields, map the composition and movement of gases deep within the planet, and detect the presence of water, a critical element for understanding the planet's formation. By doing so, Juno would help reveal whether Jupiter has a solid core beneath its swirling clouds or if its gases extend deep into its interior. The mission wasn't just about scientific curiosity, though. It was also a feat of engineering. Juno's journey to Jupiter covered 1.7 billion miles over nearly 5 years, relying on a gravity assist from Earth to accelerate its speed toward the distant planet. This gravity assist occurred on October 9, 2013. When Juno swung close to Earth to gain momentum, propelling it on a trajectory to reach Jupiter by mid-2016. The spacecraft, powered by large solar arrays instead of the traditional nuclear energy source for deep space missions, had to survive the harsh conditions of space and the intense radiation surrounding Jupiter. It was a mission that pushed the limits of technology, requiring precise navigation and robust protection from Jupiter's powerful magnetic field. Upon arrival, Juno's mission took on even greater significance. Jupiter, with its swirling bands of gas, massive storms like the Great Red Spot, and intense magnetic environment, presented a wealth of phenomena to study. The spacecraft's suite of scientific instruments, including those designed to measure microwave emissions, gravity, and magnetic fields, were calibrated to gather data from previously unexplored depths of Jupiter's atmosphere. The mission planners set Juno on a highly elliptical orbit, allowing it to pass close to the planet's cloud tops every 53 days, where it would spend hours collecting detailed measurements. This orbit not only allowed for close study but also helped Juno avoid the worst of Jupiter's radiation, preserving its systems for longer-term exploration. Juno's arrival at Jupiter on July 4, 2016, was a historic moment for space exploration. After nearly 5 years of travel, the spacecraft executed a flawless orbital insertion, bringing it into a stable path around the gas giant. This moment marked the beginning of a new chapter in our understanding of Jupiter and its many mysteries. With Juno successfully entering Jupiter's orbit on July 4, 2016, the mission moved into its critical data-gathering phase. One of the primary goals was to probe beneath Jupiter's thick clouds, which had long shielded the planet's internal dynamics from view. Equipped with an array of scientific instruments, Juno began its work, passing as close as 2,600 miles, 4,100 kilometers, above the planet's cloud tops during each orbit. These flybys, known as perihovs, gave Juno an unparalleled opportunity to collect high-resolution data, allowing scientists to study Jupiter's structure, composition, and magnetic field in unprecedented detail. Juno's early discoveries began to reshape the scientific understanding of Jupiter almost immediately. Prior to the mission, it was widely believed that the gas giant was composed of relatively distinct layers, with a potentially solid core at its center. However, Juno's measurements of Jupiter's gravity field suggested something far more complex. The data revealed that the planet's core might not be a compact, solid mass as previously thought, but instead a fuzzy or diffuse region of heavier elements. This finding indicated that Jupiter's core could be partially dissolved or extended far deeper into the planet than anticipated, challenging long-held theories about gas giant formation and evolution. Juno also uncovered unexpected details about Jupiter's polar regions, which had remained largely mysterious before the mission. Juno's JunoCam and infrared mapping instruments revealed clusters of cyclones at both poles, forming geometrically arranged patterns that puzzled scientists. The North Pole, for example, features a central cyclone surrounded by 8 others, while the South Pole boasts a similar arrangement of 5 storms. These massive cyclones, some spanning up to 870 miles, 1,400 kilometers, appeared stable and long-lasting, showing little change over time. This discovery was a stark contrast to the banded structure of the planet's mid-latitudes and raised new questions about the forces governing Jupiter's atmospheric dynamics at different latitudes. As Juno continued its mission, each flyby brought more revelations about Jupiter's complex interior, atmosphere, and magnetosphere. The spacecraft's magnetometer helped produce the most detailed map yet of Jupiter's magnetic field, which turned out to be far more irregular than anticipated. Instead of a smooth, uniform field like Earth's, Jupiter's magnetic field showed unexpected patches of intense strength and unusual structures. One particularly strange feature, nicknamed the Great Blue Spot, was a concentrated area of magnetic strength near the equator, further deepening the mystery of how Jupiter's magnetic field is generated by its internal processes. These early results from Juno revealed a planet far more dynamic and unpredictable than scientists had previously imagined. Every orbit brought new data that not only answered some long-standing questions but also raised new ones about the giant gas planet's internal mechanics, weather systems, and magnetic forces. The Juno mission, still in its early stages, was already expanding humanity's knowledge of Jupiter, helping to refine models of planetary formation, evolution, and behavior across the solar system and beyond. As the Juno mission progressed, its investigations turned toward one of the most powerful and enigmatic forces surrounding Jupiter, its magnetosphere. Jupiter's magnetic field is the largest and most powerful in the solar system, extending millions of miles into space and affecting not just the planet itself but its moons and surrounding environment. The magnetosphere traps and accelerates charged particles, creating intense radiation belts that pose a danger to spacecraft, including Juno, which was carefully designed to withstand these hazardous conditions. One of Juno's key goals was to better understand how Jupiter's magnetosphere is generated and how it interacts with the planet's atmosphere and surrounding space. Central to this investigation was the spacecraft's magnetometer, which provided highly detailed measurements of the planet's magnetic field. Previous missions, such as the Galileo probe, had revealed that Jupiter's magnetic field was much stronger and more complex than Earth's, but Juno's observations painted an even more intricate picture. The data revealed that the magnetic field is not symmetrical or uniform. Instead, it contains unusual structures, including the Great Blue Spot, a region of intense magnetic activity near the equator that continues to puzzle scientists. Juno also examined the connection between Jupiter's magnetosphere and its iconic auroras, which are the most powerful in the solar system. These spectacular light displays, seen near the poles, are caused by charged particles from the planet's magnetosphere interacting with its atmosphere. Juno's measurements showed that Jupiter's auroras are driven by different processes than those on Earth. While Earth's auroras are largely fueled by the solar wind, Jupiter's appear to be powered by particles originating from its volcanic moon Io, which constantly spews sulfur and oxygen into space. These particles are captured by Jupiter's magnetic field and funneled into its polar regions, where they collide with atmospheric gases, creating the brilliant auroral displays. Juno's study of Jupiter's magnetosphere and auroras provided crucial insights into the dynamics of planetary magnetic fields and how they interact with their surroundings. The findings helped refine models of magnetosphere formation and behavior, not just for Jupiter but for other magnetized planets and exoplanets as well. They also raised new questions about how gas giants generate such powerful magnetic fields and the role of deep planetary interiors in shaping magnetic activity. While the primary focus of the Juno mission was Jupiter itself, the spacecraft also provided new insights into the planet's diverse and fascinating collection of moons, particularly the Galilean moons, Io, Europa, Ganymede, and Callisto. These four largest moons of Jupiter, discovered by Galileo in 1610, had long been targets of interest due to their unique geological features and potential for harboring life, particularly Europa and Ganymede, which are believed to contain subsurface oceans. Though Juno was not specifically designed to study Jupiter's moons in detail, its various flybys provided opportunities for observations that offered tantalizing clues about their characteristics. One of the most exciting targets for future missions is Europa, an icy moon with a suspected ocean beneath its surface. Juno's infrared instruments captured intriguing images of Europa, revealing more detail about its surface composition and temperature variations. These observations supported the idea that Europa's ice shell is dynamic, with areas of warmer ice potentially indicating subsurface activity, such as the movement of water or the formation of plumes. Juno also provided key data on Ganymede, the largest moon in the solar system, which is unique in that it has its own magnetic field. During one of its close passes by the moon, Juno captured stunning images and made detailed measurements of Ganymede's magnetic environment. The spacecraft's instruments detected complex interactions between Ganymede's magnetosphere and Jupiter's own powerful magnetic field, offering new insights into how these two massive bodies influence each other. Io, the most volcanically active body in the solar system, also caught Juno's attention. Juno's flybys revealed more about the intense volcanic activity on Io, which continuously ejects material into space. Juno's measurements of Jupiter's magnetosphere showed how Io's volcanic emissions contribute to the planet's auroras and the charged particles in its radiation belts. These early observations of Jupiter's moons set the stage for future missions, such as the upcoming Europa Clipper and JUICE, Jupiter Icy Moons Explorer, missions, which will delve deeper into the mysteries of these distant worlds. While Juno's primary mission was focused on Jupiter, its contributions to the study of the Jovian moons have already enriched our understanding of these fascinating satellites, hinting at their potential for harboring environments conducive to life. Part 5. Extending the mission and looking to the future. As Juno's primary mission concluded, the wealth of discoveries it provided demanded further exploration. NASA extended Juno's mission beyond its original timeline, allowing the spacecraft to continue orbiting Jupiter and gathering more data on the gas giant's atmosphere, magnetosphere, and moons. This extension marked an important new phase of the mission, where Juno would push the boundaries of what it had already achieved and probe deeper into the mysteries of Jupiter and its system. The extended mission gave Juno the chance to perform more close flybys of Jupiter's moons, especially Ganymede, Europa, and Io, further enriching our understanding of these enigmatic bodies. These flybys allowed Juno to conduct a detailed analysis of their surfaces and atmospheres, gathering critical data about their composition, geological activity, and potential subsurface oceans. The closer look at Europa, in particular, was aimed at assessing the moon's ice crust and helping future missions like the Europa Clipper identify the most promising sites for exploration. Juno's continued study of Jupiter's atmosphere remained a central focus of the mission. By completing additional orbits, Juno was able to investigate how Jupiter's weather systems evolved over time, including long-term monitoring of the Great Red Spot and other storms. Another key goal of the extended mission was to refine our understanding of Jupiter's magnetic field. With each new orbit, Juno's magnetometer collected more precise measurements, mapping the planet's magnetic environment in even greater detail. The continued study of the Great Blue Spot and other magnetic anomalies provided important clues about the internal dynamics driving Jupiter's magnetic field and how it might change over time. As the Juno mission advanced into its extended phase, scientists were also looking ahead to the broader implications of the mission's findings. Juno's data was helping shape our understanding not just of Jupiter but of gas giants as a class of planets. The insights gained about Jupiter's formation, structure, and evolution have had far-reaching implications for the study of exoplanets, particularly the gas giants that orbit stars beyond our solar system. By using Juno's findings as a framework, astronomers can better interpret the data gathered from distant exoplanetary systems and refine models of planet formation and behavior. In the final years of its mission, Juno remained a pioneering presence at Jupiter, pushing the boundaries of what we know about the largest planet in our solar system. The spacecraft's legacy will continue to inform our understanding of planetary science for decades to come. As it orbits Jupiter, Juno continues to inspire both awe and scientific curiosity, reminding us of the vast, dynamic forces at play in our solar system and beyond. Through its extended journey, Juno has become a vital link in the ongoing exploration of our cosmic neighborhood, paving the way for future missions to unravel even more mysteries of the universe.